we've seen that being an isomorphism is actually a very special property for a function. And there are sort of two flip sides to that coin. One side of the coin is that it takes a lot to be an isomorphism. We might hope that checking that you have an isomorphism would be a little easier. So that's one thing that we'll think about. And another thing that we should think about is, since being an isomorphism sort of says so much about the function, you might expect that isomorphisms sort of play nicely with other facts about vector spaces or other properties of vector spaces that we've encountered. And of course that is the case, so let's look at some examples of that. So on the first point, so we defined preserving vector space structure using these two statements. So an isomorphism turns addition in one vector space into addition in the other vector space, and then scalar multiplication in one vector space into scalar multiplication in the other vector space. But actually, you can sort of combine these two, and instead of proving these two separately, it's actually equivalent to show just this one statement here. And this is because, right, to show that these two are logically equivalent, we in principle, we need to show both implications, but what we'll actually do is, right, both of these are equivalent to this down here, which is preserving finite linear combinations. So what we can do to show that all three of these are really describing the same property is we can show that if you assume A, you can prove B. If you assume B, you can prove C. And if you assume C, you can prove A. Right? So then we have this cycle of implication that can get us all the way anywhere between these three. So fortunately, all three of these implications are pretty straightforward to demonstrate. So showing that A implies B, right? We are assuming A, we want to prove B. So what is f of A1 V1 plus A2 V2? Well, there's an addition right here, and we're assuming that f preserves preserves structure for addition, so we can use that to write this as f of A1 V1 plus f of A2 V2. Right? That's using this first assumption. And then we can use the second assumption about scalar products to move the scalars outside, sort of like this. A1 f of V1 plus A2 f of V2, and that proves this right here. So we've proved that A implies B. For B implies C, well, here we have a finite linear combination. B is just a linear combination of two vectors. Well, what we can do is break this down, and I guess I need my parenthesis here. We can break our finite linear combination down into a linear combination of these two vectors, and then use part B. But then, right, now we have f of this whole mess, but then we can use part B again to break this one down into smaller and smaller pieces. So if you have n vectors, just use B n times, and you'll break this big thing down into that. So B implies C, and of course C implies F. C implies A is immediate because preserving addition is just a special case of preserving finite linear combinations where you only have two vectors and both scalars are one. So we get addition immediately, and of course preserving scalar multiplication is also a special case of preserving linear combinations where you only have one vector and some scalar. So we get that one as well. So that proves that all of these three are equivalent. So if we want to prove that a function preserves vector space structure, we really only need to prove one of these. We don't have to prove two separate things, right? These two separate statements. So that can be a labor saver. As far as special properties that isomorphisms have that sort of make them nice for vector space things, one is that no matter what your zero elements are, your additive identities in V and in W, F will always map the zero in V to the zero in W. right? And we can see that because so to figure out what f of the 0 in V is, suppose that think about this, f of some vector plus the additive identity in V. Now, on the one hand, we can do this addition in V, and we just get f of V. On the other hand, we can use the fact that f preserves structure. We get f of V plus f of 0 V. Okay, and now look, what we have here is f of 0 V acts like an additive identity, right? So since it's acting like an additive identity, it is an additive identity, right? We know that additive identities are unique, so this has to be equal to the additive identity in W because it's behaving like an additive identity. So f always maps the 0 vector in one vector space to the 0 vector in another vector space. A similar thing is that f maps additive inverses to additive inverses. Of course, you can show this in a very similar way. F of minus V, so if we want to know what does f do to the additive inverse of some vector, well, we can write this as a scalar product. We've proved that an additive inverse is minus 1 times a vector. But now we can use the fact that isomorphisms preserve structure to move this minus 1, this scalar of minus 1 outside. But now this is in the vector space W, and in W we know that one scalar product with f of V is the additive inverse of V. And so we've shown that this additive inverse gets sent to the additive inverse of f of V. All right, last interesting property, and this is maybe the most interesting of all, is that an isomorphism is totally determined by what it does to a basis. So if two isomorphisms agree on a basis, then they're actually the same function. They're the same isomorphism, right? It seems at first like, well, there are so many functions, how could you even know sort of how many isomorphisms there are? Well, what this is saying is that you don't actually have to keep track of what an isomorphism does to every vector in a vector space. You really only need to keep track what it does to a basis. Okay, so let's suppose that we have a basis, say beta 1 through beta n, a basis for V, right? And we want to assume that f and g do the same thing to this basis. So we'll suppose that f of beta 1 equals g of beta 1, and so on, right, for every basis element. So f of beta n equals g of beta n. Okay, so we're assuming that these functions do the same thing to every basis element. Now what we want to show is that they do the same thing to every vector in V. So what we'll do is take any vector in V. Since we have a basis, we know we can write our vector V as a linear combination of basis vectors. So write a1 beta 1 plus and so on up to an beta n. Okay, then now you can do a big calculation. What does f do to V? Well, V is this linear combination, a1 v1 plus a1 beta 1 plus down to an beta n. But now we can use this property that we showed up above where isomorphisms preserve finite linear combinations. So we can break this linear combination down. This is a1f of beta 1 plus and so on down to anf of beta n. But we know right now the only place where f is doing anything is to basis vectors. But we assumed that f and g agree on basis vectors, so we can turn this into a1g of beta 1, right? Because we assumed f of beta 1 is equal to g of beta 1, so we're replacing equal things here, plus dot 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 down to a n g of beta n. But g preserves finite linear combinations, so now we can put this whole mess back together all inside of g. So g of a1 beta 1 plus dot 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 plus a n beta n. And of course this is g of v. So we've shown that if you assume that two isomorphisms do the same thing to a basis, then they actually do the same thing to every vector, right? They agree on every vector, and they're actually the same isomorphism. All right, so what this is saying is that having an isomorphism doesn't require that much information. You just have to say what happens to a basis. Any basis will do. Of course, different bases will require different descriptions. But all right, last thing I wanted to say about general properties of isomorphisms is that the inverse of an isomorphism is also an isomorphism. This isn't totally obvious, so if we have an isomorphism from V to W, so is an isomorphism, since it's one-to-one and onto, we know that the inverse function from W to V exists as a function. So we know there's an inverse function. The question is, does it preserve structure, right? Since it's an inverse function, it has to be one-to-one and onto. The only question is, does it preserve structure? So to check if it preserves structure, let's remember, we only need to show that it preserves a linear combination of two vectors. That's enough to show that it preserves structure. So let's take a linear combination of two vectors in the domain of f inverse. And the domain of f inverse is W, right? When you do inverse functions, domain and range switch. So let's call our vectors W's instead of V's. So A1, W1 plus A2, W2. So now what we're hoping is that when we do some big calculation, we end up with A1 f inverse of W1 plus A2 f inverse of W2, right? This is what we're hoping to get to at the very end, because then we will have shown that f inverse is preserved structure. So how do we do that? Well, right, we know that f is an isomorphism, so probably what we want to do is somehow use the fact that f preserves structure, but to make that happen, we need to make f show up somewhere. And it's a little hard to know where to make f show up, but we want f inverse to show up right here, ultimately, right, by the time we get to the end. So one thing to remember about inverse functions is you can make them sort of appear out of nothing because they undo each other. So we can make an f inverse show up here, and an f will also show up here. So let me write down what I mean. So let's see. So f inverse of A1. So W1 is equal to f of f inverse of W1. Right? This is the characteristic property of inverse functions. If you do one and then the other, you end up where you started. So this W1 right here, we can replace it with f of f inverse of W1. And then we can do the same thing for the second term. A2 f of f inverse of W2. So this seems funny at first. It seems like, hey, aren't we unsimplifying this? Yes, we are unsimplifying this, but this gives us some more pieces in our expression to work with. Notice that this f inverse now is showing up where we are going to want it, and also now we have f showing up, and we can use the fact that f preserves structure. So f inverse. Okay, so now use the fact that f preserves structure. If you keep an eye on the stuff inside parentheses here, this is a linear combination of two vectors where f is hitting both vectors. Well, that means that we can move this f all the way up to the front of the linear combination. So we get f of a1 of the times the first vector, which is f inverse w1, plus a2 times the second vector, which is f inverse w2. And I need one more parenthesis. Okay, but now look, here's f inverse of f of some vector. Well, these two undo each other, and so you get a1 f inverse of w1 plus a2 times f inverse of w2, and that's what we wanted to show, right? So we've shown that f inverse preserves structure, and that means that the inverse of any isomorphism is an isomorphism.